Hey everybody, this is Jeff for CS161 here from Module 5. We're going to do a slightly deeper dive into conditionals. We'll cover a couple different ways to do some of these conditionals and a few more kind of advanced topics there. We're going to talk about character strings and floating point numbers as well, just in the context of conditionals, but also just a little bit more details and some of the boundary cases you may run into here. And so for Module 5, same drill here. If we jump into the overview, we're working on Chapter 5 here in the books. We got our discussion and our assignment here. So if I jump to the book, you'll see here, Part 2 of Conditionals, we're going to talk about some more advanced comparisons, right? Instead of just comparing integers, which was primarily what we did in the previous module. And we'll get into the guts of a couple specific things here as well, around floating point and strings and so on, that you'll use as well in your programming. So we'll go ahead and get started. As usual, we'll build the code here in Replit. I may or may not have anything for Visual Studio here, I forget. And we'll provide the code along with the video, which you should be able to see if you're watching this video, obviously. All right, let's talk about the switch statement. And the switch statement is a general purpose conditional. When you have a long and uniform if-else condition. Okay, and this is best, we're just going to illustrate this with an example. And if we were together doing this interactively, right, I would basically do a shout out and ask for area codes. So we'll enter your area code and let's see if I know where you are. Let's do that so I don't have a wrap. Enter area code and let's see where where we are. And so we're going to do, actually, no, we'll do the switch statement first. Let me demonstrate the switch statement first, and then we'll do it as if else as well. Okay, so we create this construct switch, and somebody yells out Portland. So area code 503 will produce a message of Portland. Somebody yells out Seattle. Actually, the only person yelling out is me, and it happens to be all the places that I've lived, right? Detroit. Oops. I'll explain what these break statements do here in a moment. Ugh. What is it? 612. Anybody know 612? That'll be Twin Cities. And let's do one more place that I've lived for more than a few months. Ann Arbor. The switch statement also has a default condition. And this is where we would say, I don't recognize that area code. You, of course, could leave that out, but I wouldn't. Now, if you were watching the cursor, you notice that when I hit return, anytime after the first character of a case statement, I'm fine, right? You see how my cursor is indented here? But after, oh, it's working now. It wasn't working before. It wasn't always indenting. I noticed with Replit, it doesn't always indent, so it's something you need to watch. That hopefully will show up as I keep editing. So let's try this. I have an extra brace. Okay, so I'll enter 313 and I get the correct answer. Run it again. There's 734. I get the correct answer. Do one more. I get the correct answer. I enter something that I don't have. I don't recognize the area code. Okay, so what I like about a switch statement is it's very uniform, right? And I see students use switch statements when they want to do a big, large set of comparisons. However, there are many cases where switch statements become obsolete, right? So they have a place, but once we learn arrays, hash tables, databases, etc., they often can be replaced with these more advanced constructs. I also see funny switch statements where numeric comparisons can be done. And I don't have an example of that, but if I had case 1 do something, case 2 do something, case 3 do something, case 4 do something, that's a signal that you can optimize this by using the value itself versus testing each value. And a little bit outside of the scope of this lesson, but I'm just planting the seed here. I cannot tell you the last time I used a switch statement in production code. And that is not a message that says you should never use them. It's as much of a message that says I haven't used them. And maybe there's a couple places where I could have or should have, but I find that there's other constructs that work better for me. Okay, so now let's talk about the break statement here. These cities have more than one area code, right? And so I could do this, case 425. So 425 is also an area code common in Seattle. So what I do here is I just add a new statement right here. And so now let's see what happens. So 503 still gives me Portland. 425 still gives me Seattle. It gives me Seattle, and 206 still gives me Seattle. Okay, so what you see happens here is that as I work my way down, I find the match. And I'm going to execute everything below the match until I hit the break statement. The break statement says to basically exit out whatever construct I'm in. So in this case, it's, the best way you can think about it is exit the curly braces that I'm inside. So I'm going to exit, this pair of curly braces. So I could put all the area codes where I want to give my answer of Seattle here. I could do, I hope I get this right. I think that's right. I can do that as well. So now I get, again, 2 responses that give me Portland. Okay, so very uniform, easy to read, relatively easy to maintain. Okay, now I could write this out as an if-then-else statement, right? And I'm going to just paste that in because it's really too painful for you to watch me type this in again, right? But let's compare it to the if-then-else, right? So here is I'm checking to see if the right area code I print, else if it's these area codes I print, else it, so on and so on. Okay, if we look at the lines of code, and let me take this out so we're doing apples to apples, we have line 23 through 42, so that's 20 lines of code, versus 53 to 65, which is 20 or 13 lines of code. So this is shorter. Okay, and Again, it's a preference thing. The switch statement does take up more visual space, but it becomes a preference, right? In terms of what you like. And the other thing that is, this is outside the scope of this class as well, is that the compiler will recognize a switch statement and it will construct the code behind it differently than an if then else, and it may be more efficient. So you may find that, especially like if we did area codes, there's thousands of area codes, maybe, I don't know, certainly more than hundreds. If we did that, we might find that the switch statement is going to be way more efficient than this 1,000+ line if else thing. But there's a better way to do it that is 200 level class material. Okay, so that's our switch statement. Some of you will find yourself using that depending on what you're coding. Okay, let's talk about next Boolean data types. Okay, we learned last week, right, that a conditional expression results in a value true or false, and the conditional will execute based on that value, right? So, for example, if A is greater than 0, this is the conditional expression, and based on the value of A, it'll either return true or it will return false. With a value of 10, it returns true, but with a value of 0 or a negative value, it will return false. Okay? And so, but you can also have Boolean data types. And so you could create variables and store the value true or false. And it's a great way to capture the status of something in your code to be used later. Okay, so for example, example of a Boolean data type might be keeping track if a piece of data meets all conditions, and when one condition fails, we set the flag to false. Okay, let's run through an example here. If we go to the book, okay, so we talk about the switch statement here. Let me talk about this real quick here. Here's an example of what the flow chart looks like for the switch statement. This is, checking the month against our 12 different months, so we'd have a switch with 12 different cases, right? If you wanted to check all 12 months. Okay, now we'll go to Boolean data type. I think I want to do 5.3.2. Well, no, that's not the one I'm going to do. I'm going to do a student age one. But 5.3.2 is a good example here. Let me do my example and we'll come back to that. Okay. All right, I know this is in the book somewhere. I must have written down the wrong example here. 5.3.2. Okay, here it is. All right, I was just missing that. Given the following if statement, let's walk through this real quick. Okay, I just pasted the code in here, right? So let's walk through it. If the user age is greater than 13 and the user age is less than 21 and the GPA is greater than or equal to 3.5, set the discount value to 7.5. Else, if the user age is greater than 13 and the user age is less than 21 and the GPA is 2.75, set the discount to 5, else set the discount to 0. So what's happening here is we're really checking two different things. We're checking to see if the age is greater than 13 and less than 21. That condition is the same in both of these lines. And then if that condition is true, if the GPA is at 3.5 or higher, we set the value to one value. If it's 2.75 or higher, and remember, we've already checked a greater than 3.5. So this is really, the 5.0 is between 2.75 and less than 3.5. We set the discount to 5. Otherwise, we set the discount to 0. Okay, whenever I see code like this, the first thing, if I notice that you have code that is duplicated in two places, this is a risk of a bug. We try to avoid this at all cost. Okay, so let's run this. Make sure it works. No, it's not going to work because I didn't enter the age. Oh, we got to enter this too. Okay. I don't have prompts, so we'll just kind of pay attention here. We know what to do here. Okay, we'll enter the age of 14. We'll enter the GPA 399. And it's not working. Let's make sure. I have the prompt in the wrong answer. Let's see if this works. All right, my code's not working. I'm going to pause here for a moment. All right, I think we're back live. Sorry about that. Let me confirm we're running here. Yeah, we're running here. Okay, it would help if I printed out the results of the code here. Okay, so we're gonna enter an age in the window and a GPA that's above, and we get our top discount. Let's try an age that's invalid, so regardless of the GPA. And if I do an age that's valid and I do a different GPA, 3 of the test cases that I would run. Now remember, I talked about when you test this code, you want to test at all the boundaries. So I test at 13 and 14, 20, 21, 22, 3.5, 3.49, 2.75, 2.74, etc. and run through all these. Now, like I said, I got code that's duplicated, which means if I realize that I meant to do that, less than or equal to 21, and I forget to do it here, my code doesn't work anymore. Or if I change 13 to 14 and I forget to change it, because your code won't always be, your 2 lines that are duplicated won't always be right next to each other. They may be in different functions. They may be spread across different files. They just may be later in the code. And so it's dangerous. Okay, so a good way to work around this here is we create a Boolean data type, and we'll call it valid age. And we're going to say valid age is equal to the conditional expression that we're using there. Okay, so valid age is going to equal the result of testing user age greater than 13 ANDed with user age less than 21. So then I simply say valid age here. So now when I run my code, it works. Okay, let's double check for both cases, right? 3.0, and it works. Okay, so code is more maintainable. I have a flag or a Boolean status that I've set that I can use throughout my program, right? Because you may find that you might have a valid age and you might disqualify it or requalify it in other ways. Okay, by eliminating the duplicate code, we've made our code simpler and easier to maintain and likely less to have a bug. Okay, I've also seen, by the way, you know, you don't have to use a Boolean. You could use an integer, right? You can say if this is true, set valid age to 1, else set valid age to 0. Or you could use a char. If this is true, set valid age to y, else n. Or yes or no. You can do any of that, and that's all okay. Um, the Boolean is the most efficient. Okay, so let's just take, so for example, I could say if expression flag equals yes, right? And so you can have a descriptive name if you want, or it could just be a Boolean. I would encourage you to try the Booleans, right? And so this is our example here. You should be able to go through this now. Couple other examples here in this section. Okay. All right, let's talk more about strings. Okay, we don't have really a section on strings, so the book kind of covers it in stages here. If you remember from last week, remember that these are not the same, right? Even when you print them, they look the same. They're not, because this trailing space is right here, right? Okay. So that's just a reminder. But now let's look at some other examples here. Okay, so we take two Alexes and their full names here. Let's do this. If S1 is less than S2, okay, pause here and get a show of hands. Who thinks we'll see the do we see this message? We don't, because I have an error somewhere, because I forgot that. And we see it. Okay, so what's happening is we're doing a relational operator using the alphabetical order of the characters in the string. So we get to this character here, which is different. So the A, L, E, X, A, and D all matches. And then since the letter E is before the letter R, S1 is deemed as less than S2, or it's earlier alphabetically. Okay, we can do the same thing with upper versus lowercase. This one may be less obvious. I need Replit to recognize my common errors and just remove them for me. We don't, right? So we should number these. So we see number 1. Let's run this again. We see number 1. We don't see number 2. Okay, so why is this? All right, remember that characters are stored in binary in the ASCII format. So let's look at an ASCII table. Let's take a look at this one. Lowercase a is a decimal value of 97. Uppercase a is a decimal value of 65. So the uppercase characters are less than their equivalent lowercase character. And in fact, even uppercase z is less than lowercase a. So I have this backwards, right? So it's the S2 is actually the smaller string in this case. And we do see it in this case. Okay, so we can do string comparisons. This is how you, if you had string data and you needed to sort it, this is what you would do. You learn sorting in Python in CS160, where you learned insertion sort, and selection sort. If you wanted to sort strings, this is one way you could do it. Moving a little bit away from the relational operators, but because it is covered in the book here. Okay, so we have some examples of string comparisons. Here's our example here. In this example, right, we have people with the same last name, and we're then alphabetizing by first name, right? So Amy shows up before Joe here, right? And so some examples here. The next section of the book talks about some more ways to poke at individual things inside strings. Okay, remember we start counting at 0. Okay, remember this was learning for a lot of students in CS160. We start counting at 0 in almost all cases when we're doing things in programming. So I'm going to create a string. Okay, hopefully I got that right. And so I can say the first character is okay. What I have here, this is a new construct here. I have this period following my variable name. What that means is I'm going to apply a function to that variable in place. And specifically, it's what character is at that position. So let's try that. The first character is A. Okay. Now, if I didn't place this reminder for us, you might have just done that. The first character, 1, but that's B. So remember, we start at 0. Okay. Therefore, if I want to get my Z, I have to use 25. And let's see what happens if I do that. I get an error message. I get a runtime error message here, right? So the program runs, and when it gets to here, it says I've terminated because I have a out of range error. Okay, and I'm trying to access position 26. My string is only 26 in size, so position 26 is 1 extra, because a size 26 string has positions 0 through 25. Okay, just like in binary, if I have a 4-bit binary, I have 16 values 0 to 15. All right, so 16 is too big. Okay, so remember that we start counting at 0. Let me show you another function we can use. Okay, again, I'm using a function using this dot mechanism. Size size 11. Let's confirm that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so again, our size is 11. That capital H is at 0, and the last E there is at 10. Okay, I can also do this. This is a little different syntax than what we're used to, right? We're used to saying S2 is equal to something. But what we're doing is we're using this append here, and we're changing S2 in place. And you can see here that my S2 is now there. In fact, I can do that here. If I do that, let's see what happens. Actually, I have 4 exclamation marks because I appended 2 here and I appended 2 more here. Okay, so this is, just keep in mind here that when you use the S2 append, you're modifying that string in place. The at and the size are queries, so they're not modifying. They're operating on the string, but they're not modifying. Okay. Some more examples. Nope, let's do care. No, not a care data type. Okay, we're not using that yet. And this is a alphabetic care. Of course it's a care data type. I've declared it as a care data type. Okay, this is alpha. You know, what do you think is alpha is going to check for? Let's look. Should be intuitive here. Here's our at as we walk through the book. More ats. Here we go. True if alphabetic A through Z or capital A through Z. Makes sense. Should be intuitive here. Okay. Care C5 equals 5. Just copy that. Numeric character. I don't like that. It's a care containing numeric no, it's a numeric care. Numeric care. Remember, this is not the number 5. It's a character data type with the ASCII value 5 inside it. Right? And we can do that by saying we run the int function around it. Normally I would do the static cast, right? And you see I get 53 here. And if we go back to our ASCII table and we find 53, here's 53 right here. And it's the character 5. So that's our is digit, 0 through 9. There's also is space. I don't think I need to demonstrate that. I want to demonstrate the 2 upper and 2 lower though, because there's some interesting thing that happens here. Okay. Two upper. Okay. Let's print this guy out and see what we get. Let's see, case 1, CZ. Okay, show of hands, right? How many people think you get a capital Z? Most of you will raise your hand, and half the time I'll raise my hand too and then realize that's not right. It is right. Sorry, I have my numbers out of order here. Okay, so since I've declared CZ as a character, when I convert it, it stays as a character data type. But if instead I do this, kind of giving away what's going to happen here, I get the value 90. And if I again go to my ASCII table and I find 90, I get my capital Z. Okay. So 2 upper and 2 lower are functions that return integer values. And you'll get an integer value unless you directly or indirectly cast the result. And so these are like the 3 ways we would do it, right? We would declare we'd run the function into that data type. This is the simplest way. Or you can cast the result and get the same answer. Let's run this one more time with some consistent formatting here so you can see this. Okay. This is a bug that sometimes people will fall into a trap here. Okay. All right, let's do a couple more string things here. Oh, I lost my alphabet. Let me go find that and paste that back in. Okay, so here's our alphabet. Now I'm going to, in place, I'm going to run the find command. Let's see what we get when I do that. It gives me an answer of 9. So let's look at that. Starting at 0, let's count until we find the letter J. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. J is the 10th letter of the alphabet, but remember we start counting at 0. Okay. Doesn't matter in this example string, it doesn't matter if I have JKL or just J, but what if I have JLK? I get this bizarre value right here. Okay, we'll come back to this in a second. This means it didn't find it, right? If you look at it, right? But this number means something. We'll come back to this here in a second. Okay, if I have another example, I'm going to look for O in this string. I get 4, so I get 0, 1, 2, 3, 4. It finds the first O. We'll talk later in this, not today, but in the next weeks to come, we'll talk about how to find all the O's, or the second O, or the last O. We'll figure out how to do that. Right now, what we've learned is that find finds the first instance of that substring in your string. Okay? And so we can do that using loops, and we'll learn about that soon. Okay, so now is getting tricky. I'm going to run with this replace function on my string. And if you look here, I've replaced F, G, H, and I with the letter Z. So again, starting at position 5, which is the 6th letter, which is F, I replace 4 characters with this string. I can also do this. So I go to position 13, again, starting from 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I went too fast. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So at the 13th position, which is where the Q was, I insert this string of M's. Okay, these calls are modifying S1 in place. All right, so you don't need to say S1 equals S1 dot replace, blah, blah, blah. You don't need to do that, right? And so it's a little bit counterintuitive. All right, last topic for today. Let's make sure we didn't miss anything before we jump to it. Some examples of these manipulations. The find command. I didn't cover substring. You can do that. You can do that on your own. We talked about adding strings earlier in the class, so you can give that a try. And we didn't try replace either, but now you basically will know how to do that as well. Okay. Here's some searching. Some good search examples. And some more on comparisons. There's a different method of a conditional expression, which I'm not going to cover. Okay, that's what this conditional expression is. It's this obfuscated thing, which is a way to simplify using an if-then-else. I just want to make you aware of it, but I'm not going to cover it. It's here in the book. All right, let's go down to floating point. We have talked only a little bit about how floating point numbers are represented in binary. I think I mentioned that in CS160 we used to cover it in more detail. Floating point is an interesting problem because not all numbers are perfectly represented. Okay, and I think this is the example in 510. We'll come to that here in a moment, right? But let's first set ourselves up with a large decimal point here. And this is an example in the book. Okay, I took 0.7, I subtracted 0.4, that get me 0.3, I subtracted 0.3, that should get me 0, right? Let's see what happens. Instead, here, let's shorten my output so we don't have this wrap, which might confuse people. I don't get 0. I get negative 0.0000. I have lost count of how many zeros, 5551. Okay, so I have a precision accuracy issue here with doing relatively simple math here. These are not complicated numbers here. Okay, so if I say you'd think that I'd see this message because I've subtracted, I've taken my wood, I've cut it, and I have 0 left, but I don't. Okay, so let's try to understand why this happened. We're going to convert 0.7 to binary. Okay, and I have this worksheet that I've made in Excel. Let's walk through this here. I'm tempted to just clear all this out, but let's do this instead. Put this stuff in dark gray here. So let's focus on the text that's not yet, that's basically has the dark gray wrong. When we converted decimal to binary, right, we did the power of 2 flippy-do exercise, right? If you wanted to convert 27 to binary, you first said, okay, 32 is too big, so that bit's 0, 16. That bit is 1, so I subtract 16 from the 27, and I have 11. Then I subtract 8, and I have 3, so I skip 4, and so on. That's the flippy-do exercise you did in CS160. But for decimal values, we do it as powers of negative values that are going up. So 2 to minus 1, 2 to minus 2, 2 to minus 3, and so on. We're dividing by 2 with each bit. Okay, so some simple examples are 1/2 is 0.1. And if I cut 1/2 in half, it's now 0.1, it's 1/4, that's 0.01. And so 3/4, which is 1/2 plus 1/4, is 0.11. There is a reason we don't cover this anymore in detail. Okay, so if you're following, awesome. If you're kind of following, awesome. If you're not sure, that's awesome too. It's not a big deal. I'm giving you some background information to show why the code is failing. Well, the code is working, but why you think it's failing. Okay, so if I take this and I expand it out, 2 to the minus 1 is 0.5, 2 to the minus 2 is 0.25, 2 to the minus 3 is 0.125. Each of these values I'm dividing by 2. And if you look in my Excel, I'm taking 2 to the power of that negative number. Right, so 2 to the minus 10 is 0.000977, and it actually is more digits than that, right? More digits, and then it finally, right? So these digits, right there, there's a lot of digits here, right? Okay, so if I want to find 0.7, I have to start from the left and work my way right. 0.7 is greater than 0.5. So I'm going to put a 1 in that position, right? So these numbers are going to be the numbers to the right of the decimal point. Okay, so I'm going to have 0.1. Then I subtract this value from 0.7, and that gives me a remainder of 2. I check that against this position. 0.2 is less. So then I put a 0 there. So now I'm at 0.10. Okay, that's where I'm at so far. I'm not, since that's 0, I just propagate my current balance, and now I compare that to 0.125. 0.2 is more than 1.25. In other words, I have room for 2 to the minus 3. So I'm going to add a digit there. Sorry, it's a little clunky the way I have this set up. And then I subtract 0.125 from 0.2 to give me a remainder of 0.075, which is enough space to fit 0.0625. So I add another digit. I subtract this from that, and I get that. This number is smaller than this number, so that's 0. So I add a 0 here, not a 9, a 0. I propagate the remainder down. This number is smaller than that, so I add another 0, and so on. So now we've done 11 positions. And this number right here, 0.000292969, it's not, I don't know. This number may eventually end, right? If we did this 1,000 decimal points, it may end, or it may not. If you dive into this floating point representation, you will find some very simple numbers are irrational when they're represented in binary. Therefore, you will always have a precision error. Just like if you are trying to deal with 10 divided by 3, 9 divided by 3, or 1/3, or the square root of 2. Those are irrational numbers, and eventually you'll run into kind of some accuracy problems. Okay, so what we have to do is we have to recognize here, if we jump back to the code here, let's print out here, let's do this. We're going to print out the number after each assignment. Let's see what we get. Okay, so we get 0.699999. See, we've underrepresented 0.7 because we had some remainder so at some point we stopped and we had a remainder left. That's why our number is lower. Okay, and then when we subtract 4, like this part looks right, but notice what happened is like we also altered some stuff down here. And then when we subtracted 0.3, these last digits changed as well. And so this is showing you that all 3 of these numbers have a problem because they all modified those last few positions by some amount. If I add some more decimal points here, you'll see that, we're kind of just, it's bonkers here, right? We have a level of inaccuracy here that we probably don't care about, right? And so in big math or little math, right, we have this concept that we talk about. Well, before I get there, there's 2 ways to manage this, right? One way is to round these numbers. Like after every sets of calculations, you round the number. Okay, you can do that, right? You can round the number. The problem is not advised because A, extra operations you may not need, and B, more importantly, you may propagate errors and make them worse. Right? We've all done this in real life, right? We're doing math in our head and we round something early to make the next math easier, and then we've kind of propagated that error. Okay? And so don't do that. Instead, we need to allow for some amount of give. Okay, so for example, the distance between Earth and Jupiter is 365 miles plus or minus 1 mile. Okay, so I'm basically saying that, like, I'm setting an allowable amount of error to be less than a mile, right? And so I'm saying the distance is 365. It might be 364.1 or it might be 365.9. It's somewhere in between there. Okay? And so this is called referred to as epsilon in typical math. In fact, I'll show you the Greek letter because it's in here. I can't put it in Replit. Well, maybe I can. Actually, we'll try. All right, I missed it. There it is. I know it's in here. I thought I saw the character. Maybe not. Maybe not. Okay. Greek epsilon is this guy right here. This it looks like a letter 3, or it looks like a number 3, right? So let's see if I can paste that into Replit. Oh, good. It lets me. Okay. No, it doesn't. Maybe it does. Okay, so referred to as epsilon, typically a very small number, right? This astronomy example was just to show you when you're doing big math. But when we're doing this kind of stuff, we want to just check, like, no more than 5-6 digits, right? If we're doing physics, we might do 10 digits, right? Okay, and so we're gonna set epsilon to a relatively small number. I think the book suggests this. I'll add one more 0. Doesn't really matter. Actually, I won't. Doesn't matter. Yes, I will. Doesn't matter. And so we'll set the epsilon value. Now I can say if num meters is less than epsilon, okay, with epsilon. I'm going to run that and see if that works. Okay, it did work. Okay, this is not correct yet, because if num meters is negative of any value, that'll still be less than epsilon, right? So what we have to do is we have to take the absolute value of num meters and compare that to epsilon. Okay, and that works. Okay. So when you're doing floating point math, and if you're ever doing equality comparisons, you need to take this into account. If you're doing less than, greater than, it doesn't matter, right? Because if you're checking to see if you're less than 1, it doesn't matter if you're 0 or 0.0000551, whatever it might be, right? But if you're doing equality, you need to get in the habit of doing this. And a good practice is to put that inside a function call in your own libraries, right? If you're doing a lot of this in more advanced programming. Okay, and so that's what we're showing you how to do here. This is, you could see here in this code, I'm checking number of meters minus 0. The minus 0 is not needed, right? Because we're comparing to 0. But if we were comparing to something, like if we were comparing number of meters to 10, we would subtract from 10, or we'd subtract 10 from it and then check to see if that's within epsilon. That's what this example is showing. Okay, this is interesting. Let's double check. Yeah, it looks like the numbers are, yep, the numbers are the same. So Replit is replicating to exactness, which makes sense, because there is a very standard way these numbers are measured, or are represented rather. Okay, so some examples here for you to go through to try to get this down in detail here. I don't remember if this section is part of the content or not, but it's some cool additional stuff that we used to cover. And every now and then I get these questions about, hey, I did this floating point and it's not working, and it's I'm using simple numbers, but it's not equal 0, right? So I think it's worth doing. All right, I'll get this posted, and let me know what questions you have, and we'll talk soon.